Yeah, you know what? Hold on. Speaking of that, yeah.
So is the homework going to be due on Tuesday?
He doesn't have it today.
The second learn.
I haven't even posted it yet.
Uh-huh.
No.
Okay. Great.
So, yeah,
Monday?
probably not.
Probably not.
More like Tuesday after that.
Uh-huh.
Yeah. Or maybe, I mean, it's not going to be that much. We can make a smaller homework that's due on Tuesday so that we can
Okay.
keep up. But it's not like you're going to have to invest more than like 2-3 hours.
Yeah, that's okay. I love doing this, so it's fine.
Yeah.
Never mind. So we will run several algorithms, SVM. What else did we cover? Nearest neighbor, Bayesian, decision tree.
Yeah, so decision trees we're covering today.
Are we covering today?
Yeah.
Okay. So then we can run all of those on one
I
second.
mean, you can run whatever you want there, really. That's the nice thing about it.
This particular set.
Yeah. I mean, scikit-learn. I'll pull it up. Yeah, so basically, if you go to, I guess, examples, and for classification, you'll get a whole bunch, I think. So, yeah, this is SVM with the different parameter. We could do some validation on that. There are plenty of others. You could use a linear model. You could even do an ensemble if you wanted to. So, for example, decision trees, you can have like one decision tree or like multiple decision trees that work together as an ensemble. I think they should probably have that. Yeah, so for example, like a random forest classifier or random tree embeddings or random forest regressor. So these are all possibilities, and then what else is there? You can use these, I guess, the multi-class ones, naive Bayes, nearest neighbors, neural network. There's plenty to be tried out, like then SVM.
Should we try neural networks even though we didn't cover them?
You don't have to. I mean, if you wanted to play around with it. I think what we're gonna definitely do is even we haven't like talked about it in detail yet, but like we're gonna say that we're gonna have a support vector machine that you can try, and we're gonna like define a few parameters that need to be validated, like
The different gammas.
yeah, so different C's, maybe different kernels, and then maybe different gamma values. But like it's not really that useful to like if you know how to validate for one parameter, you know how to validate for multiple. And then there's like this nice one, I think there's a grid search, yeah. Yeah, so that's kind of cool. Maybe we're gonna use that. So grid search, it basically helps you implement, for example, if you have to update multiple or you validate for multiple parameters. The grid search like basically tries all combinations for you and like spits out the best combination, so you don't have to like basically write a double for loop and identify, or like a triple for loop or whatever. And I think it might actually have some smart smart algorithm in there that it doesn't try every combination, but it like does some smarter search for you. So like that's all possibility.
That's very cool. That is very cool. Would it plot what it tried? Because you will ask us. My guess is that you will ask us what we tried and what is the best one. Not just the best one.
Yeah, it will tell you what the best one was. You get the optimal parameters, and then you have to reuse those optimal parameters afterwards. I think it spits out, or it returns the optimal set of parameters. And there's a user guide for it.
Cool.
Yeah. Okay. Great. So let's do a little bit of decision trees. I think everybody's calmed down. It wasn't that hard, was it? It's just a few checks that we need to make. All right. So decision trees, we talked about like what they're being used for, and that they can be used for classification and regression, and that they're again a non-parametric method that is trying to basically split, divide and conquer, help us understand the world better, and like they're split up in decision nodes and leave nodes, and in decision nodes we conduct a decision function that basically allows us to split the tree into like yes or no sides, and what we're trying to do is we try to find leaf nodes that are as homogeneous as possible. They have like as little entropy as possible, so that we have a good like subset of our data set in those leaf nodes, and can make a good decision of like what's going on. We assign classes to these leaf nodes depending on like possibly the majority class, or just the only class that's left in those leaf nodes. Alright, this was an example, and we're going to talk about the univariate ones, where we only select one dimension at a time to make a split or to make a decision in our decision tree. So to split the input by like one dimension at a time. We could do multiple dimensions at a time, but that give us a more like expressive tree. It would be just a one level tree. We would find a perfect solution if we like find a diagonal through here, but we don't really want to do that right now, yeah, so we just focus on the univariate ones for now. So so if you look at the entire data set right now without the splits, you can see that it is not homogeneous, right? You have multiple classes, so the entropy in this data set is not perfect, and you have well, you have a higher probability of circles than for squares, so the entropy wouldn't be like 0.5, but it would be like something lower, okay? So once you split this off here, you have one side which is now going to turn into a leaf node where the entropy is going to be 0, because there are no other data points in this part anymore, and so we have gained the highest like entropy gain making this split. And so we have no entropy here, but also we have not as much entropy anymore in this side. So this side is also not as like heterogeneous anymore. And we have a number of so the majority class now is squares rather than circles. And if we find this split here, we can now split that into two homogeneous samples. And this is kind of like the idea behind the decision trees. We're going to walk through those, that we want to find those splits that optimize the entropy, okay? So we had those facts, and now we're going to talk about the univariate trees, where in each test only one input dimension is used, and if input dimension j is discrete and used in the decision node, then the decision node checks if the input xj and implements an n-way split. So like if we have a discrete dimension that is like just like a color, blue, green, or red, whatever, we can make decisions like where in the univariate tree we would have multiple splits and 3 regions in our branching. But what we're mostly going to focus on is if we're going to deal with numeric splits, where we basically just decide to have like a threshold function greater or equal or smaller than, and then we just have a binary decision of yes and no, and we split up into those separate regions. So we have a left region and a right region, and basically we're going to reiterate the same procedure onto these subregions until we identify a great, the best tree. So tree induction is the process of learning this tree, and obviously, like as you've seen in the previous example, like if we put the threshold anywhere in between those regions, and if these are real numbers, we can put them like really anywhere, and so that means like we have basically infinitely many like locations where we could split this up, and but we don't want to just get the we just want a good tree rather than the perfect, and the perfect tree obviously has many solutions in that data set. But one of the things that we want to keep in mind again is we don't want to have the tree to be too large. So like you can always come up with a solution where the tree doesn't make zero errors on your data set, unless maybe like 2 data points that are exactly equal have 2 different labels, but that hopefully doesn't happen. But you can always come up with a perfect tree that is like super complex and has only 1 data point in each leaf node, but that's not what we want. We want to be able to generalize, we want to derive rules that make sense. So we should keep in mind that we only want like a certain depth of our tree, and we only want a certain width of the tree as well. The finding of the tree, or the optimal trees, is NP complete, so you can imagine it's quite expensive to calculate, but there are search algorithms that function quite well, and if the data is looking quite good, and we have these checks and balances and say like, okay, we only want to have a certain depth of the tree and a certain width of the tree, we can find our solution quite quickly. The usual tree learning algorithms are greedy, so they try to make the best split at every single time step. So they identify like where to like split the data perfectly for this current subset of the data, and we try to recursively reiterate this. But now let's define what is the perfect split, and we talked about this a little bit. For classification trees, the best split is quantified by the impurity measure. An impurity measure could be, as I said, entropy, it could be Gini index, it could be max likelihood for a certain class in a split, and so on. We want to also define the word pure. So a split is pure if after branching off we only have one class in one side of the node. For the formal definition, so node M is reached. That basically means like a data point trickles through the nodes or the tree, and if it reaches node M, that is basically, that means just that this now is defined as the root node, and the number of data points that reach this node are is just this number nm to the power of I. So it's the number of samples that reach node M and are of class I. Okay, so these are just a number of items that we have that are of one class versus the other class, and then we calculate, for example, the probability that the items belong to one class over the other class within that node. So we want this to be, for example, 1, and for all others 0. So that would be the definition of a pure node. So pure nodes here. This one's not pure. This one's not pure. These three are pure. Okay. And then typical impurity measures are, as I said, the entropy, for example, which is basically just defined as the probability for each class times the log 2 of the probability for each class, and you sum that up over all the classes. In our case, it would be 2 classes, for example, and basically you can visualize the entropy as such, and it has a maximum value of 1 when the split is basically 50-50, and you don't really know which class you're gonna have in there. And you would try to make the splits that improve or reduce this entropy maximally, so that we, for example, would reach a 0, or so that the probability of a certain class to be in that node to be 0 or 1 for the other class. All right. And so we try to like find the splits that optimize this criterion the best. Yeah, and just for your reference, like entropy basically just specifies the number of bits that we would need to identify a certain code, or it's like a bit, and if the likelihood for a 0 or a 1 in our code is equally as likely, we would always need a full bit to understand that this is
So it's a Hamming distance?
No, it's basically, so for example, if you, like a code is optimal if you need less items to write the number, or like to write the message. So for example, like Morse code is has a lower number of bits, and like it has the lowest number of items that you have to send over your channel, because it basically follows the likelihood of like how many times does the letter E happen, and so like for the letter E you only have one item, but then for like more like rare letters like W and it's like 4 or 5, yeah. So this is kind of like basically based off of like information theory, and it's basically if you listen to a channel and for every bit that you receive, you have to know the full 1 or 0 to know what the message is, or do you just heuristically know, okay, like 70% of the time it's going to be zeros, and you don't have to like send that much information over the channel. Yeah, so other impurity measures, you can come up with many of them. Basically, if we have a perfect split between the two classes, so where like each class is most likely, then this needs to be larger or equal to any other split. So this basically means that this impurity measure, like, and this is if you want to come up with your own measure, this impurity measure is maximal if the likelihood for each class is equal, right? Then it is symmetrical, so you can have like each class split over, and and this value is also increasing for the range of 0 to 1/2, and it's decreasing for 1/2 to 1. So basically you will have to have a curve like this to define an impurity measure, and there are other impurity measures that follow this. So we had the entropy. The Gini index works as well. It's a little easier to calculate because it doesn't have these logs in there. And then you can also just use a misclassification error, which is basically 1 minus the max of those two probabilities. And these are both for k equals 2. So like the number of classes is equal to 2, but you can expand those to multiple classes, especially the entropy is pretty easy to extend to like n classes. Yeah, and it doesn't really make a difference which one you use. All right, so, and what we're trying to do in the tree induction now in classification trees is the following, so that basically what we try to do is we try to find the one the impurity split that optimizes or the split that optimizes the impurity measure after the split. And so basically we define that like NMJ now is basically after we are in node M, or we take one of the like J branches, like in our case most of the time 2 branches, and so basically what this satisfies is that the sum of like the number of items that we have in an M is equal to the sum of all the branches that we're taking, or like equal to the number of items that are in the branches, so we're not losing any, and NMJ with the I on top is again like the number of items in that branch that belong to class I, and now the new probability, if we make that split, basically is defined as such, where we try to, or we basically have the probability of this class I in our new like split off branch divided by the number of total items in that branch, and the impurity after the split now is defined as such. So what we need to make sure here is that, so we want to make the right decision that minimizes our impurity, but we don't want to just always cut off like one item at a time. And so what we need to do is we need to weight the entropy with the number of items that we have. So in the example that we had, if we start off with a where would we make it? Yeah. So if we start off with the first split like this, right, we would have a homogeneous group down here with just 2 circles. But that's not the optimal split, because while we have a pure set down here, we have a very large impure set up here. So just cutting off a few items that are then pure doesn't like it's not really as valuable as if we cut off a big chunk that is impure, or that is pure. Okay, so we want to maximize the number of items in each pure split. So what is it? This is what's happening here. It's basically over all the branches. You weight the entropy with the basically the mass of that subset. Okay, so you want to have a large subset that you cut off with a minimal entropy. Okay.
Because basically, if we would split the bottom two ones, we will have worse entropy because now you have closer, actually more impurity.
Right,
You
in the larger group, yeah, but in the smaller group
yeah.
you have a better.
So because this is actually looking into after the split,
Yes.
the entropy that is weighted by what is left.
Exactly. And so what you want to do in the end is basically you want to look at IM, so the entropy before you make the split, and you want to subtract this new entropy dash, IM dash, and you want to compare those two. Like you want to compare the global entropies rather than the local entropies. And that's why we need to weight this entropy with the mass of each split. And so this basically then comes down to an algorithm where to generate the tree, we need to identify if the node entropy is less or equal to a threshold. And if it is, well, we basically are done. We can go back. So this is our recursion break. But if it's not, we split the attribute. And split attribute now defines, okay, which attribute are we going to use to split? And basically, first we set it to max, our minimum entropy. And then for all attributes, so we identify like for all the d dimensions that we have, if the xi is discrete with n values, like we split into x1 through xn by xi, and we identify the split entropy. And basically, the split entropy is the equation that I just showed. So how big is that entropy now? And if E is less than the minimum entropy, in the first step it's going to be, so we set it to minimum entropy, and then we say, okay, this is I is the best split. And if it's not discrete, if it's numeric, well, we do the same, but we do it with a smoother split. And basically, we just return the best split, or the best like dimension to split with. And for each of these splits now, we find the different branches, and we basically go through this again. And so the defined entropy, we basically look at this entropy for each of them, and we try to find the one that is minimal here. Okay? And yeah, so this is a bit complicated if you want to program that because of the recursion. But in the end, what you want to try to find is the items or the dimension that splits off the best chunk and has the best split entropy. So, and the split entropy again is like the entropy, the new entropy after splitting the data into these chunks that has the right weightings. Okay?
Can we split more than once under each node?
That's the problem with the univariate nodes. Like you cannot split more than once. So, but you could define very complex functions in there. You can have as many functions in there as you want, but it becomes more and more complex then. You had a question as well?
Oh yeah, so for the numeric split, would we decide like the numeric value based off of like going past adding one more data point or something?
Yeah, so what you would do with the numeric splits, you you can define, so as we said, like you can have this split anywhere in between here, right? So what you would try out is you would compute the split entropy for, in this case we have 2 dimensions, so you would decide if this line here is the best or if this line here is the best. And so what you do, you go through all of them, you go through every single data point, and you just add lines just above them, right? You wouldn't have like, okay, I split it here, and then I try every single one of them between here, but you just go from one data point to the other in that dimension, and just put the line everywhere where the data point is, and say like, okay, what is this now, what is that now? Okay. So it basically grows with the number of data points you have. I think you can do some heuristics where...
Just let me know right now.
So obviously like this, like finding the optimal split grows with the number of items you have. If you have categorical items, such as like color, like where green, blue, and red, you would just test on like the 3 attributes, but with numeric ones, you have to go through all the data points and just decide, okay, is this dimension the right one here, or is this dimension the right one there? So yeah. So basically, you what this says is you find the best like location xi to split, and in this case, you decide like which attribute to split with. Yeah, that's a bit complicated, but in the end, it's not too hard. And we'll see how to do that in a second. Again, caveats that we can have with these decision trees. Overfitting is a big problem. We decided already, like we said already, that like if you make the tree very wide, you can have in the end like each leaf node to have like just 1 data point. So you can always perfectly fit your training set, but that's not what we want to do. And we want to find like the right like size or complexity of your tree that fits your data set. There's some criteria or some strategies that we're going to talk about in a second that basically allow you to prune your tree as well. So you can take off like branches off the tree if they don't really help you. If you can merge leaf nodes with others, there are some possibilities to that. All right, but let's talk about an example here. So basically, we want to know if John plays tennis. And here are our here's our data sets. We have like 14 days, and we want to know if he's going to play on the 15th day. And we have weather outlooks: sunny, forecast, overcast, or rainy. We have humidity high or normal, and we have wind strong or weak. And so we only have like categorical items. So when does he play? And we can find out, like we can build a decision trees. And the first split that we're going to do is based off of the outlook, because the outlook, if we split it into sunny, overcast, and rain, gives us the best split, and I'll show you how. So basically, we have our outlook. We have 9 yeses and 5 no's, so 14 in total, and the entropy is pretty bad in this case. And if we split it up into sunny, overcast, and rain, well, we can see the following, that these 5 days fall into the sunny category, these 4 days fall into the overcast category, and these 5 fall into the rain category. And in this case, he was playing twice, and 3 times he didn't play. In this case, he played 3 times, and he didn't play for 2 times. And here, he actually played 5 times, so this becomes a pure set. So that's kind of like where we're going to stop already. And then for the sunny case, we're going to split on humidity. For the rainy case, we split on wind. And basically, we're going to have 4 pure sets down here. And basically that defines our tree, so he's going to play. Because we have rain and weak wind, so he's going to play. Okay. So you can play this through if you want to. You would just have to calculate the entropies and at each decision step and decide like which ones are the best. And here, for example, all the weights, like these total number of items in each branch of the node are the same. So it's like always 5 nodes, and we have a pure one here and the same entropy value on both sides here, which are pretty bad there, but it turns out that it's easy to split on that after one more split. So this is kind of like how you build decision trees. There are also regression trees, so they're allowing you to basically decide like not what class value, but what numeric value you're going to return, and we're going to see how those work. And I think we can make a 10-minute break. We're already past 11, and let's do a brief 10-minute break and come back at 11:20.